Okay, this is a video on special cases when solving systems of equations. Most of our scenarios when solving systems of equations are like case one right here. Two lines, they intersect, or two functions intersect, and they share one point. And that one point is the one solution that this system has. So exactly one solution because they have exactly one point in common. The lines have different slopes because they're behaving differently, which enables them to run into each other that one time. But then what I want to talk about is case two and case three here. Case two, the two lines are laying directly on top of each other, so they all those points are shared. And when all those points are shared, that means all those points are solutions to each other's equations. So that means they actually have infinitely many solutions. So many that we can't even count because every single point is in common and every single point is a solution to either equation. The lines have the same slope and the same y-intercept because they're the same equation. All right. Now they might look different because they might have different factors and anything that you can pull out, but the ultimately when you simplify, you end up with the same exact equation, and that's why their lines are the exact same. So that's an infinitely many solution, and we'll do an example where we deal with that. Then case three is this parallel scenario where the lines don't touch. They never intersect, which means they don't have any points in common, which means that they have no solution to their system. There is no point that is shared. So the lines have the same slope, which guarantees that they're behaving the same way, but they have different y-intercepts, indicating that they're crossing the y-axis in a different location. All right, so we've got exactly one solution. That's when they cross once. We have infinitely many solutions. That's when they're right on top of each other and they share every single point. And then we have no solutions. That's the parallel scenario. All right, let's do a couple of examples together so you can see what this looks like when this shows up. All right, so we're just going to substitution for that first one because y is by itself. So we're going to solve this equation. I'm going to take the y value and plug it into that y value in the first equation. So I've got 56x plus 8. And instead of y, I'm going to put negative 7x minus 4 equals negative 32. Again, that substitution is what I'm using in number one. If you'd rather do elimination, that's totally fine. Distributing the 8 now. So I've got 56x plus 8 times negative 7 is negative 56x. If you wanted to put minus there, that's fine. 8 times negative 42 is negative 4, sorry, is negative 32 equals negative 32. Okay, let's get the x's with the x's and the numbers with the numbers. And something strange happens. These cancel, and I'm left with 0 minus 32 equals negative 32. I'm going to add 32 and I get 0 equals 0. Well, that's a little strange because everything canceled out. But the good news is that 0 equals 0 is a true statement. That's 100% true 100% of the time. So it actually did not matter what the x or the y values that I may plug into this function are because everything ends up canceling out because ultimately what you find out is these two equations are the same thing. If you take a look here and you solve that top equation for y, you would get that equation on the bottom. All right, so real quick, I'll work that with you. We'll subtract 56x from both sides. And this is just trying to get y by itself. Those cancel. I've got 8y is equal to negative 56x minus 32. And then I'm just going to divide everything by 8 in order to get in order to get y by itself. Y is equal to negative 7x minus 4. And that is the exact same equation as that is there. And when they're the same equation, that means the lines are laying right on top of each other, which means that these have infinitely many solutions. All right, infinitely many solutions. So everything canceled out, zeros equals zero. If you end up with a true statement like that where everything cancels out, that's a clue that this is an infinitely many situation. Okay. Now number two, we'll use elimination here. Actually, we could do substitution pretty quickly just by adding one. So I'm going to go with that. Change plans. Y equals 3x plus 1. I'm going to take that and I'm going to plug it into the top. Okay. So negative 3x plus, and instead of that y, I've got 3x plus 1 is equal to negative 3. And now I've got negative 3x plus 1 is equal to negative 3. And now my 3x's, if you add those together, they cancel. And I've got 1 is equal to negative 3. Well, that's not a true statement. 1 is not equal to negative 3. 1 will never be equal to negative 3. So because that's a false statement, that's a clue that this is a no solution situation. And if you take a look, that was the equation y equals 3x plus 1 when I solved for y on the bottom. If I real quick solve for y on this top equation, I'm just going to add 3x to both sides. And you'll end up seeing why there was no solution. Y equals, because those canceled, 3x minus 3. You see that here and here, the slopes are the exact same thing, which means these lines are parallel. And if they're parallel, they never touch. And if they never touch, they never have a point in common. So lines that are parallel, they have no solution for their system of equations. So that's the two scenarios on how they might show up. So for infinitely many, everything cancels out, but you get a true statement. For no solution, everything cancels out, but you get a false statement. And again, you can always check back and see in the infinitely many solutions, the equations are the same. In the no solutions, the equation or the lines are parallel because the slopes of the equations are the same. I hope that's helpful. Pay attention to these things as you're solving in case you ever run into one of these special cases.